So this is the Unit 7 review for circuits. And like usual, I'll be looking over in this direction every now and then to see if anybody's chatting. So let me know if you got questions there. I will look over to my right to see if anybody's got any questions on my phone for the Remind app. And I mean, just generally, I'll be looking around a little bit. So it doesn't really matter though, because I'm just a little spot in the side bucket. What's really important is what's up on the screen here. So as you can see, starting out with some note card ideas. This is sort of, I won't say the minimum, but it's definitely just a start. So if you don't have these things, these are just things I came up with off the top of my head. As you're going through the review guide, if you have anything else you want to write on your note card, obviously you have lots of room, and you'll have time in class tomorrow to work on your note card if you need it. And so as you're going through your review guide, if you see anything you want to add to your note card, feel free. This is just some ideas that I came up with. Obviously the three main equations that show the relationship between voltage, current, and resistance. Power equations can be nice, and then voltage is just charge per time. That's not even right. Let me erase that before anybody gets that wrong. That is that's not time. That's current is charge per time. So how many charges go by per second would be it. Boy, that was up there for a while. And of course, the rules for circuits, which I did not write here. That will take a little bit of room. That's like, in a series circuit, that current is the same everywhere. It splits up when you get to a branch, but in a series, the current's going to be the same. And then, of course, the function of a battery or any power supply does not add charges. It just moves the charges. It acts like a pump for the electric charges, the electrons that are already in the wire and in the circuit. So make sure you're familiar with those kinds of things. They're kind of captured a little bit on the review guide. So I'm going to use the review guide as sort of the focal point here. If I think of anything else off the top of my head or as I'm going, I will mention it. But of course, at the very beginning, you have to be extremely familiar with the basics here, the stuff in this table. If you're not, you're going to have a hard time. It's going to be a bad test. Hopefully by now you're pretty familiar with it, but it's always good to review and reset. So better blank that out. Okay. So not really much to say here. It's pretty straightforward, units and all that stuff. Just make sure this is on the key. So if you don't quite get this from the video, you can always check the key that's linked on the OneNote. So okay, so without further ado, what is necessary to cause a current to flow through a conductor? Well, I mean, you need some sort of voltage. I'll write this here. I'm not going to write every single thing. You need that electrical pressure, so voltage, also known as the potential difference. Potential difference. Okay, it's just like, for water to flow, you need, for water to flow downhill, you need an uphill and a downhill. Otherwise, water is just going to sit there in a puddle. And that's what happens with electricity, where you have to have one side that is higher than the other. But instead of gravity, instead of higher in location, it's higher in pressure. Like the electrons on one end of the conductor have to be crammed closer together. You have to have higher energy. In other words, again, think of electrons being smushed together like rubber balls being pushed together. The closer they're pushed together, the springier the more energy is stored in the rubber balls, the closer they're pushed together. And it's the same idea with electrons, in a way, is that the closer they're pushed together, those negatives are repelling each other. And so one side of the conductor has higher potential energy, and the other side has to have lower. So you have that high voltage, and it's going to move to the lower voltage. So that's what you have to have. You have to have that potential difference. So whenever you have a battery, you have the two terminals, and one side is high and one side is low. And same thing with an electrical outlet and any kind of power supply. You're going to have two sides, one high and one low. The potential difference, one high energy and one low energy. That flow of electrons is called current. I guess I'll write that, but you should probably know this by now. I guess it's good to review the basics. amount of charge per second, well, that goes to that one equation that I had written earlier. That is just also current. Okay, that's like, you know, how much water goes by per second is the water current. This is the electrical current. Conductors and insulators, I'm going to leave that. I'm not going to write anything right now, but it's on the key if you want to see it. I mean, you can just Google it too, but I mean, basically conductors allow electrons and charges to flow through them. Insulators do not. So make sure you know that, you know, metal is a good conductor. Things that are, I mean, for all intents and purposes, wet. I mean, not pure water, but anything that's has water in it is going to be a good conductor. And insulators, things like glass, plastic, rubber, wood, anything that's an insulator of heat will typically be an insulator of electricity. It does not allow electricity to go through. What types of materials make good conductors? I pretty much just said that. Good conductors is metal, copper, gold, iron, that kind of stuff. So, all right. Now, for number 7, I just want to point out, you got to make sure you read these questions carefully. All right. Which one's going to have the least resistance? That means it's going to have it's going to slow it's going to actually not slow the electrons down. The least resistance, it's going to have the lowest resistance. And so it's going to allow more flow. You're going to have the higher current, and you're going to get that in a short and thick wire. Okay, so read the questions carefully and think it through before you just jump to an answer. Because if I look at that too quickly, I might have chosen a long and thin wire because I feel like it's going to have the most resistance, and so it's going to have the least current. And you know, you start to second guess yourself, but too quickly for you to notice. So just take a second, think it through, make sure you got the question and you're answering the question that you are actually being asked, and not the question that you think you're being asked. Okay, it's not a trick question, but sometimes we see things that aren't there, so watch out for that. Okay, 8, 9, 10, and a bunch of others then are just all going to be variations of the equations from above, the V equals I times R equation. And in fact, that's what this one's all about. This one gives you, so again, I'm not going to spend too much time on this. This is going to be a quick review, by the way. But as long as you know that this is resistance, and this actually tells you it's current, so this is going to be current, and it wants to know how much voltage it's going to be. It's a pretty straightforward question. Now, if you're asked these on an FRQ, you better show your work. Okay, list all the variables. So you're going to be like R is equal to, and it might seem like kind of a, I don't know if a waste of time is it, but it's going to seem unnecessary because these are basic type questions, and that's okay because you need to know the basics too. So you would actually list the knowns and the unknown, the givens and the unknown. Okay, you would be like, well, okay, V is I times R, so you'd list the equation, you would substitute, so I is going to be 20, and it's important you do this, even for the ones that you think you know, that you think you got a good handle on, like these basics, especially during a test or any type of situation where there's higher stakes than normal. You just want to make sure you dot all your I's and cross all your T's. And it's easy to mess this up. It's easy to divide when I should have multiplied, or multiply when I should divide, or who knows what, because you think you know what you're doing. And you probably do, but that's when you get complacent. And so just write out the question. Just take the extra 10 seconds and write everything out. All right. Even if it's not being graded for, you know, showing your work, it's still not a bad idea to do it. I mean, you've seen me make mistakes on the board. I make mistakes all the time, and I'm much older than you. And so, you know, I feel like I probably know what I'm doing, but still, it's easy to make a mistake. It's easy to just mess things up. So I'm done preaching about that, but I'm just going to tell you, make sure you show your work when I ask you to show your work, especially on a free response question. 9 and 10, like I said, are pretty much just variations of the same thing. So the answers, in case you didn't notice, are down here. So hopefully I got the correct answer, and I did. So 200 volts I multiplied. All right. Not seeing any questions just yet, and that's okay. So I'm going to move on. You'll notice that this page here, again, it's more of the same. 11, 12, 13, 14. In what, 13, no, 12, we're going to start getting into power. So that's going to be the P equals IV. So it's asking for power. You got current and you got voltage. So P equals IV. I'm going to just write that for now. So you multiply those together and you get your answer. Question 14, I believe you had to sort of figure out the current before you could figure out, but that's okay. It's a two-parter. Actually, I might as well just do it. So 500,000 or 5,000 volts, and you've got a 10,000 excuse me, 10,000 ohm resistor. So 10,000 ohms, and wants to know the power is the question mark, and P equals IV, and we don't have I, but we do know that I is equal to, oh, this is where we make a mistake. So V divided by R. So make sure you know that. You got it written down. You can figure it out. Double check. So I is going to be equal to V over R. So 5,000 volts divided by 10,000 ohms of resistance. And that's going to give me, what, 0.5 amps. And so now I've got I. And just, basically plug it into the P, into P equals IV now, and go from there. All right, and I believe, yeah, the answer is at the bottom of the page. So that's how you do that. You just got to look for what you can find, and sometimes you have to work backwards, and that's fine. Just think through it. Just think through it. All right, so that's how you do that. And all the ones above that are just variations of the same type of thing. Going forward then, and like I said, message me one way or the other if you have a question. Either use the chat or use the Remind app. If you have further questions and this is not, answering them, you can ask me in class tomorrow. You could use the Remind in the future, whatever you need to do if you're not watching this live. So 15, there's multiple parts. This is basically, you need to be familiar with series and parallel. You should get 100% on this part right now, because it literally is, well, it's, this is parallel and series. So parallel, let's start with series. Series, like I said in class, it's like you watch a Netflix series, you're going to watch all the shows in a row, all the episodes in a row for them to make sense. And so if I were to draw a series circuit, and I'm just going to draw an ugly one really quick. Yeah, I'll just put 3 resistors on there. The electricity leaves the battery, it goes around and goes through each resistor in turn. So there's only one pathway, so I mean this first one right here would be a series. And as you add more and more light bulbs, that's more and more resistance. And so it's, I use this example in class briefly, but it's as if, somebody forgot something in the cafeteria, somebody forgot something in the auditorium, and somebody forgot something in the library. And as a class, we all had to get out of the classroom. We all had to go to the cafeteria and stop and pick up the thing. And then we had to go to the auditorium and stop and pick up the next person's thing. And then we all went to the library to pick up the next person's thing and then came back to class. It would take a long time because we're all going in the same route. It's just an analogy. So there's, it's not a perfect analogy, but it gives you the idea that the more stops you have, the more resistance, the slower everything goes. So that's why for letter B, it's going to be dimmer every time you get it, because the current is going to slow down more and more and more every time you add another light bulb. Now, when it comes to a parallel circuit, if I were to do this, basically now everything has a different path. Everything parallel just means that everything's got a different path. There's choices to make, and you could draw it however you want. And I'm going to draw the most simplest parallel circuit I can imagine with those 3 resistors from before, where when the electricity leaves the battery, it has 3 choices. Basically, it's like walking down the hall. You just went up the elevator, you're walking down the hall, and you've got 3 choices of stairs. You can just start walking down the hall, and you could go down these stairs and go back to the elevator. You could walk down the hall, and you could go down these stairs to get to the elevator, or you can go down these stairs to get to the bottom floor and go back to the elevator. So no matter what, you are, you've got the high electrical potential, you've got the high voltage, higher I should say, the relatively high, And then no matter what path you take, you're going to get down to the bottom floor and you're going to be at the lower potential. And so it really is all the same. And so when each resistor has the same voltage, that just means that it's the same difference in potential energy from high to low. And because these are all the same energy level at the top, and this is all the no energy level basically at the bottom, no electrical potential energy, or at least relatively none, this is going to be our parallel. Okay, so it's the same voltage across each resistor, or at least across each path. So as you know from experience now, you might not just have one resistor there. It might, like, you might have different things going on in those branches, but in each branch or in each pathway from one side to the other is going to be the same voltage. Now, the same idea here, it's like this, you know, instead of the earlier example, now we leave the classroom and we basically split up. So the people who need to go to the cafeteria and pick up what they need will do that, and then they're going to come back to class. And then the people who go to the library are going to pick up their stuff and go there and then come back to class. And the people who need to go to the auditorium are going to go to the auditorium, pick up their stuff, and go back to class. And because we're all taking different pathways, there's no, like, they don't affect each other. You don't have to make all the multiple stops. And so, in fact, adding more and more pathways is actually going to lower the total resistance, because now there's fewer people in the hall, and so you can move even faster. Again, it's an analogy, so it's not perfect, but it gives you an idea. The more pathways you add, the more faster everything can go. And because of those extra pathways, like if the people going to the auditorium get stopped by security, that's not going to affect the people going to the cafeteria or the library, because they're on their own different pathways. So if one bulb goes out in a parallel circuit, the others can remain on because the other pathway doesn't affect them. Now the current going through each resistor is the same. Again, that goes back to our series. That's going to be the series one, because again, like, everybody goes the same path, and so everybody's going to, like, every resistor or whatever is going to have the same current, the same amount of electrons going through per second. And finally, letter F is going to be our parallel, again, because you could add a switch, like for example here, and you can shut off some of the light bulbs, but the others one will stay on. It sort of goes back to letter D, you know, like letter D, where one light bulb goes out and the other ones could stay on. So again, make sure that you're familiar with that stuff, and just, you know, make sure you got it. Make sure you understand it. You might need to go back to the FET simulation to review that kind of stuff, but that's okay. Do that if you need to. All right. 16. Draw a circuit diagram. Schematic diagram. I guarantee you, you're going to have to draw one, and I also guarantee you that you better use some sort of a straight edge. I'm going to get mine out of my little junk drawer over here. Okay. And when you draw it, make sure you use a straight edge. What I drew up here would be acceptable, but you would not get full credit because I drew it freehand, and you could just tell it's not super duper neat. Okay. Now I'm not going to draw this because, well, it's on the it's on the key, and there's several different ways, many different ways you can draw this. All right, but keep them square. Okay. One thing I did do correctly here is there's no diagonal lines, there's no curvy lines. It's just not, I didn't use a straight edge. So for both of these, it's the same idea that you want to stick with whenever you're drawing a schematic diagram, circuit diagram, is make sure that you, whenever possible, use straight, horizontal, or vertical lines. All right. So I purposely made this circuit sort of like wobbly so that you can sort of use your own imagination and how to do this. Now, one thing to keep in mind is that the schematic diagram just shows the connections. You could, for example, take this bit right here. Orange is not going to work very well, but you could take this bit right here, and you don't have to actually draw it as a single wire. You can literally draw it like, you can make it whatever you want. If you wanted to draw, and I'm obviously butchering it, but you can draw it like that is the same exact thing in a schematic diagram. You're just drawing the connection. You're not, so I would not have this anymore because that would be a short circuit. But you're just drawing the connection. So don't feel like you're constrained to the geometry of the wires as they're actually there. You're just going to draw the connection. The same thing here. I have a kink here, I have a bend here, and you don't have to have that there. You can take that away and draw a straight line, or you could add more bends. It's like whatever you want to most clearly and best represent the connections in this circuit. Okay, so use pencil, because you're not going to get it the first time, I guarantee you. Maybe you will, actually. I guess I can't guarantee you, but you may not get it the first time. So use a pencil when it comes to this. Bring a pencil to the test on Wednesday and an eraser, because you don't want to have to worry about not being able to erase. Okay. Moving on. Oh, I skipped a whole page. Not do that. Oh, well, it's actually a good page to skip. So this whole page, this whole third page, is more practice with the equations. Just try them out as many as you need to. The answers are just like before. They're on the bottom. They're also on the key. Nope, they're not on the key. I don't know if I did many of these on the key. A couple things to note is where I drew the arrows. Like you saw in the lab, a lot of times measurements of current is going to be below, like it's going to be a decimal. And so it's very common to measure current in milliamps. And when you have milliamps, you have to divide by 1,000, you know, so this is actually going to be the equivalent of 0.150 amps. All right. And whenever you do the equations, you're going to use amps, not milliamps. So just watch out for that. And then kiloohms, I mean, kilo means 1,000. If you're walking a kilometer, that's 1,000 meters. So in this case, you're going to multiply by 1,000 to go to kilo, so 60,000 ohms. All right, so just look out for those types of modifiers to the units there. All right, I was looking, there's not really much else. 23, 24, a little bit of a situational type of thing. What's going to happen? Again, just use the math to figure out what is going on. And 24, I'll let you think about that a little bit. I mean, how does voltage relate to current? If you push twice as hard, what's going to happen to the current? And then what's going to happen to your cell phone if you plug it into something, a bad connection? The squirrel and bird, those things. This question is a tough one in some ways because it might not be very clear. I don't know. The thing to keep in mind is, I mean, there's a couple of things here, and I'm not going to write anything down, so I'm just going to talk about it. Is in order to complete a circuit, you have to have a loop. And squirrels and birds on a wire, they're only touching one wire. They're not touching the ground usually. They're not touching any other conductors. And so if you've got high electrical pressure, but there's no place for that electricity to go, then the circuit's not going to be complete and you're not going to get a current. And so the squirrels aren't going to get electrocuted. They're not going to die. Same thing with the birds. And you might be like, well, what if they got 2 feet on there or 4 feet? It's the same idea. They're still, I mean, between their two bodies, it's like if you stand, in a creek or a river, well, not a river, you stand in a creek, a river too, but it's a little more dangerous, is it's not like the water is going to be significantly higher on 1 foot, at 1 foot compared to another foot, because there's just effectively no difference in height for the water. So, when water flows downhill, you're basically there's not much of a difference in height from where you're standing that close together. And it's the same thing with the birds and the squirrel. Their feet are so close together, there's just not really any effective potential. There's hardly any potential difference between their feet. And their feet and skin and scales, or bird scale, but whatever, their skin has such good enough resistance that whatever like tiny itty bitty voltage or potential difference there might be between their feet is not enough to push through their skin, and so they can't get electrocuted. So I guess to boil it down, 1, there's not enough of a potential difference between their feet. You could almost say there's none. And 2, whatever potential difference there might be, it's not enough to push through their skin. So their feet are good enough resistors. Their skin is good enough resistance to to prevent a current from going through their skin and through their body. So now if they were to touch another wire or they were to touch the ground, well, now you have a very, very high potentially a very high potential difference where the energy in the wire compared to another wire actually might be enough that they could push through the skin and electrocute the bird or the squirrel. So, but if they're just on one line, they're fine. All right, no questions about that or anything else so far. We're on the last page and we're only 25 minutes in. Beautiful. Okay, graphing. This is like one of the first things we did this unit is we graph voltage and current. Voltage versus current. And all I could tell you is, here, use the graph determines the resistance of, when you have a voltage versus current. In fact, let me just put this here, because this might actually be something you want to add to your card. I don't know if you don't remember it, but even if you do remember it, you know, sometimes you blank on the test. And I know I've been there, you've probably been there too. You blank on stuff. So for a graph of we'll say voltage versus current. Okay, whenever you have voltage versus current, the slope is resistance. Okay, the relationship between voltage and current is resistance, and that sort of not even sort of, that's very much reflected in the equation V equals or R equals V over I. I mean, if you take the change in Y over the change, or change in V over the change in I, the change in voltage divided by the change in current, that's your resistance. And so that is basically what we're saying here. Now, when you have a graph, you'd want to try to typically avoid using equations like this because graphs aren't always perfect. And so you want to find the slope if you can, because the slope is going to take into account any differences and is going to make things more precise and more accurate. Okay, so in a voltage versus current graph, the slope is the resistance. And so load 1 has a higher slope and therefore it's going to have a higher resistance. So I will just say find slope for this question right here. Okay, now you do that actually here. Don't write find, I mean you can I guess, but make sure you actually find slope to find the resistance. And then, well, what is the current running through each load at the electrical potential difference is V. So now you found the slope, aka you found the resistance, and it gives you the voltage. So now you can find the current, okay? I equals V over R. And so you've got the voltage given and you've got the resistance from the slope. And so here I'll just make a note, I equals V over R, where the voltage is given as 500 volts and the slope is the resistance. So I spelled it out pretty much as best I can right there without actually completing the problem. So you've completed the problem and you'll be good. All right. The last question there is asking for the voltage and it gives you the current. So it's the same idea. You have the slope, aka the resistance, and so you just solve it. All right. Everybody's favorite part. Well, it's the last part we did anyway. And I think a lot of you guys do enjoy this. I know I enjoy it, at least at some level. It's nice when there's no pressure involved, such as a grade. So I hope you can appreciate this in spite of that part. But I know you want to be successful every time you try it. And that's important. I'm just going to say a couple things about this. And then I'll... because I don't want to spend too much time working through this. There's other ways to, here, let me just say what I was going to say. Just remember, what I do is I write the 3 main equations on there. Okay, 4, I guess, if you count power. So V equals I times R. And this one's not even really used, but it's there. I'll write it anyway, just to be complete. VR equals V over I. So those are the 3 main equations, and I always write those at the top so I don't have to worry about them. And then, you know, the little hanger on it, as I call it, the P equals IV. So that's important to know too. That way you don't have to think about them every time. Just so do that. Get in the habit of writing that at the top of your page or on the top of your scratch paper or whatever. And the other thing is look for the rules. And to summarize, I guess, I'll say in a series, the current is the same. And this is simplifying it. And the voltages add up to the total. Voltage, here, you know what? I'm going to be fancy about it. And I'm going to write the sum of the voltages is equal to the total. Okay? So the sum of the voltages is equal to the total. So if you add up the voltage for this resistor, and this resistor, it's going to add up to the total voltage, whatever that may be. All right? So, which you will have to find because you're going to get the total resistance and use the current. The other thing is, so that's current, voltage, and resistances. So for resistances, what I write on the board, sum the R's to find total. All right, I'm kind of squeezing this in here. Look on the OneNote. I took a picture of the board that one day that has the rules a little bit more neatly spelled out for you. So for a series, that's basically the so-called rules here. And I'm not going to tell you how to do this right now because I already have a video on the website or on my YouTube channel about how to solve simple circuits like this, simple series circuits. And I want this to be a shorter review session, so I'm not going to refer to that. I might put it in the notes for the video on YouTube, but it's linked on the OneNote right now. And so the key's online as well for this. So if you really want me to show it to you, I can show it to you individually in class. For a parallel circuit, parallel, the rules are slightly different where the current adds up to total. I hate trying to summarize these, but basically, I'll just kind of here. So the current going through this branch, the current going through this branch, and the current going through this branch are all going to add up and go to the battery. And so whatever the current that comes out of the battery, we'll start from there, I guess, start back over here, is going to split up. So if we all got in the elevator and we got to the top floor and we walked down the hallway, and some of us went down this stairwell and some of us went down the hall and down this stairwell, and then some of us went down the hall and went down this stairwell. It's the same number of people. We split up. May or may not be equally. It depends on the size of the stairs. And then we all came back down to the bottom floor and we got together again in a big group, well, in a line or whatever, and we went back to the battery. So the current going through all three of those is going to add up to the total current going through the battery. That's the rule for circuits when it comes to parallel circuits. For the voltage, so I'm going to try to word this carefully. Voltage for each branch is the same. So from one side to the other, in this case, is going to be 12 volts. So it goes up 12 volts and then it goes down 12 volts here. And it goes down 12 volts here. And it goes down 12 volts here. Because if you got on the elevator and you went up 12 stories and you found the stairs that takes you down to the bottom floor, you're going to go down 12 stairs, whether you take this stairs or you take this stairs or you take this stairs. All of them are going to take you down the same number of stairs, number of flights or stories. And so now again, later on, you can see down here, things can get more complicated, but so that's why I said each branch, because you might have other things going on in this branch, but the total for that branch is going to be the same as the total for every other branch. All right, and you've seen these types of things in other questions and other practices. So I can't emphasize this enough. Go back if you're still having trouble with this and do those earlier practices before you skip ahead to do this kind of stuff. So do the practice on current, do the practice on voltage, do the practice on resistance, and you'll come back and you're going to be stronger at this stuff. You're going to be more ready for these more complicated the circuits, okay? Because everything that you do there is going to culminate in these types of things. And all you got to do for these types of circuits where they're a little bit more complicated is you have to look at things in the different parts that you see. So in this case, we have a three circuits, 3 resistors wired in parallel. So you have to find the total equivalent resistance of those 3 right there. All right. And then after you do that, you can find the resistance of the whole thing. So you're going to find the resistance for everything in this red circle, and then you're going to add it to the resistance up here, the 50. All right. Now, sometimes you're going to see other resistors, like for example, maybe there was another resistor right there. All right. If that was the case, if there was another resistor, then you have to, that went flying away. Then you had to find the resistance for those first. So this is some other resistor right there. If in the case of a more complicated circuit, you have to find the resistance for those 2 in there. If there was another one, so I'm not saying there's one in here, and then you find the resistance for the whole thing, and then you find the resistance for the entire thing. Okay, so work your way out. Work your way out from those types of things. Again, I've got more YouTube videos that focus specifically on these types of questions, and I'm going to refer you to those. All right. Or we've got a few days before the test, so you can come talk to me. Okay. So I'm not seeing any questions being asked, and that's fine. I'm sure you'll ask them if you have them. So I think I'm going to wrap it up. I'm just going to put this back up here, and I'll put this back up here because, again, you want to be familiar with all this stuff. Oh, I added some things since the beginning. So you want to make sure you're familiar with these things. Add whatever you want to your note card. All right, so I just folded that back a little bit. And practice. These things are going to take practice. Practice the math, and then practice the circuits. Okay, there were 7 practices for circuits for a reason. I didn't do it because I thought you were bored. And I didn't give them to you in just any old order. So go back and practice them in order, and you will have a much better time with this, okay? And then check out the other videos I made showing you how to do this. So I'm going to wait a second, see if there's any other questions. And I'm not seeing any, so I'm thinking I'm going to end this right now. So test is on Wednesday. If you have any questions, just please let me know. So